this is like some lattice. Shastri is softer than that, actually, yes.
Yeah, very nice.
I mean, when you have pictures, sometimes you can blame them on your kids, but in this case, it's entirely me, so I'm really sorry about this. So yeah, thanks for saying you like the title. It's a very vague title. It gives me license to talk about more or less anything that I like. And what I like is to tell you broadly about topological magnons for the first few minutes. And then I'm going to tell you about some recent work with student Alberto Corticelli at PKS and Roderich Mösner. This is essentially about symmetry in relation to topological magnons. But at the same time, I'm going to flash up work with various other people who are shown here. This connects to, Caitlin's talk. It connects to work that Libor presented yesterday, some new kinds of groups or little considered kinds of symmetry groups. I'm not really committed to getting to the end of this thing, though, so just ask questions and let's see where we go. Okay, so I didn't really know where to start, so I thought I'd start really right at the beginning. So the context here is we're considering periodic lattices. When you have these periodic lattices, quantum mechanics dictates discrete energy levels. Periodicity dictates that you have a zone. We're going to consider the full zone. We're not doing long wavelength physics here. We're doing the entire K-space. When you have these discrete levels, when you have the zone, you have a degree of freedom that allows you to sweep out energy surfaces or bands in this zone. And the wave functions, for this you need to have some coherent quasi-particles, whatever you like. Most of the work in this area is on electrons, but you can have bosons instead. And the wave functions, this is just to indicate that there are well-defined quasi-particles. There should not be too much damping. There should be just some well-defined band structure. And then when you have you have a wave function associated with each point in K-space. This is a representation of K-space, which is periodic. And it turns out that, there's an internal kind of flux that one can define. I'm going to, for people in the know, I'm going to talk about Berry curvature and Chern number. Essentially, what you can do is sweep out a loop in K-space, and there's some notion of flux that cuts through or pierces this loop. For a two-band model, you can just view this as some kind of charge sitting at the center of this Bloch sphere, and there's some kind of flux going through some loop. This loop maps to this loop on the Bloch sphere. And because this is periodic and this is periodic, if I want to cover this entire region, what this amounts to is an integer number of coverings of this, which can be 0. So I can sweep out this entire zone, and you can get cancellations here, so just cancellations to a point. But it can be that this sweeps out the entire sphere, giving you number plus or minus 1, and this is a Chern number. This sounds extremely arcane, but it actually has observable consequences. If the number is non-trivial, if it's non-zero, then if you take this kind of real space slab with a non-trivial topological index, there's a bulk boundary correspondence that generalizes beyond this Chern number that tells you if you have these non-trivial bands in the bulk on the surface, this is the projection of these bulk bands onto the surface, there's some kind of edge state that is protected by this topological index. So that's the sharp signature of this kind of winding number or band topology. Now, there are sharp differences between fermions and bosons. Much of the work is on fermionic systems, and for people in this community, one thing that they really like is the existence of quantized responses. So the fact that you can populate whole bands gives you transport coefficients that literally depend on some dimensionless parameters, essentially some dimensionless so the elementary unit of conductance times some integer, which is just the Chern number of all of the field bands. This is a really remarkable result in theoretical physics, but the fact is the band topology makes itself felt even when you're away from this filling through some continuously varying all conductance. And this similar thing is true in bosonic systems because we don't have charges anymore. What we should look at is instead heat current, and this is why we look at, say, kappa xy, the thermal Hall coefficient, and this thing is now weighted by something that's related to the Bose factor, but then this flux that I was telling you about appears in here. This is now no longer quantized, but you get some smooth signature anyway. Now, coming back down to magnons, it turns out that it's rather easy to write down models with some kind of magnon bands with non-zero Chern number. Just to give you one example, if you just write down the famous Kitaev honeycomb model and then add symmetry allowed terms on particular kind of lattice, including Heisenberg, which is always allowed, or these kind of these symmetric off-diagonal exchange couplings called gamma, you can end up with a completely non-fine-tuned pair of Chern bands for any magnetic field orientation. So we have a polarized phase, and say we take the moment pointing out of the plane as shown here. So you have a pair of Chern bands with plus or minus 1, which leads to some kind of thermal Hall signature. Let me get a better view of this. So this is a calculation, as you can see, of kappa xy over t, and this is smoothly varying in temperature just because the Berry curvature is. And it shortly after our paper appeared, we were delighted to see that in one of these Kitaev systems, alpha ruthenium trichloride, that completely independently they had looked at this and seen that there's a thermal Hall signature within some window when you imply an in-plane field, killing the long-range magnetic order. You know, the origin of all of this, as alluded to as described by Kathleen, is that you have some spin model that you bosonize, you end up with complex hoppings. These lead to the band topology and this kind of signature. This is a very interesting system. These kinds of measurements in here, revealing this thermal Hall, somewhat controversial. This kappa xy is just allowed by symmetry, so kind of a hardcore theorist might go home after this. But at least for me, the mechanism is kind of interesting, and there's quite a lot of controversy over the nature of the mechanism. So as Max mentioned in his talk, there are reports of a half-quantized plateau in there, which, if true, is extremely exotic, a signature of a chiral spin liquid in the system. It could hardly have any other interpretation if it's true. More conservatively, there are magnons or phonons involved. If there are phonons, there should be some magnetic coupling. A natural magnetic coupling is just to magnons. When you go to high fields, there's a Zeeman splitting. This means thermal depopulation of these levels, which leads to this fall-off in the thermal Hall. This is the experimental data, and or representation of experimental data, so what you get is this increasing signal as you populate the levels, but this falls off because of the Zeeman splitting, yeah, you do get this signature entering into this ordered phase where
where's the quantized regime in this?
the quantized regime is actually in here. There are widely varying reports, so it's actually a low temperature phenomenon. Living in here within some regime of field and temperature. It should be a plateau in both over some regime. Okay, I mean, so actually I should mention that the Ong group in Princeton reports that there are almost flat magnon bands. So what they do is they take their thermal Hall data and then they take a model very much like the one that I put up before, but they flatten out the magnon bands. And then they claim that their data is consistent with integer quantized, not half quantized Chern number, which would be consistent with having some kind of magnon Chern bands. So I would say at the moment this is a good contender. These topological magnons are a good contender for what's actually going on in the system, though as I said, it's somewhat controversial right now. On the other hand, as has been discussed this morning, the existence of this kappa xy is not a signature on its own of non-trivial topology, and to see that in these kinds of systems, what you'd want to do is directly resolve somehow the chiral surface states in these systems, and which is a terrible experimental problem. Just by almost sheer coincidence, it's just too low energy for RPEs, knocking out electrons and doing some kind of spin-resolved measurements, or it's too high energy for NV centers. Usually these are in the terahertz regime. These are microscopic neutral things, so it's extremely hard to find a suitable coupling to them. But if it were possible to do this, I think it would just be a tremendous way forward for the entire field. After all, if you could detect these microscopic surface states, essentially magnons living on a 1D surface in a 2D material, or say a stacked Chern system and 2D surfaces, then what you'd have is a way of probing magnetic excitations in quantum materials in 2 dimensions, and there are very attractive reasons for going down to these magnetic layers on substrates. For example, you would boost quantum fluctuations. There are nice prospects for getting into strongly correlated regimes. Alternatively, you can get complex magnetic textures because of the long-range couplings induced by, say, the conducting substrate. So I would say the rewards would be very high if anybody could do a measurement of these topological surface states. So I'd say it's a nice direction to go into for this kind of larger goal. There are some ideas for how one might do this, including, say, tunneling directly through the magnetic layer into the conducting substrate and using inelastic magnetic scattering. So I just told you about gap topology, and I told you seeing gap topology is hard. There's an easier kind of topology to see, which is just where you have nodal lines or points in the bulk of the Brillouin zone. So for example, here we might consider linear crossings with nodal lines here, which have now been observed in very many materials. And these have a robust signature of topology. So just seeing them on their own, just a dispersion relation, is less interesting, at least for me, than seeing signatures of winding in the wave function. And it turns out that neutron scattering is a very nice probe of these kinds of things. So the neutron scattering cross-section, so scattering these neutral particles of magnetism, measures this dynamical 2-point correlator. And it turns out that this effective Hamiltonian in the vicinity of these linear touching points leads to winding of the intensity around these points in this way. So high to low to high, and anti-phase in the lower band. And here's some data for these different materials. A Dirac point here, extended into a line in the C direction. And here's the signature of the winding. This is a nicer picture of it here, showing this winding of the intensity in the upper band and in the lower band in antiphase, and for all four materials. And it turns out that there are interesting interaction effects as well. I'll be very brief here, but it turns out that around these linear touching points in the presence of magnon decay processes, one can view this as a linear spin wave problem plus contribution coming from interactions that is necessarily non-Hermitian because of the damping of the magnons. And it turns out that this universally gives you a winding of the line shape, not of the intensity, so of the magnon lifetime in exactly the same way as winding in the intensity. This is yet to be seen. Interaction effects can also be important in other ways, as Alex has demonstrated in recent papers. their interaction effects can lead to bound states. This is an old result, but those bound states can themselves hybridize with single magnon states, opening up topological gaps. Okay, so that's kind of a review of topological magnons, and now I'm going to quickly tell you about enlarging this picture of linear touching points and churn bands to a much larger class of topological states, and trying to find an efficient way to see, to identify materials or diagnose topology in materials. And the motivation for this is just a massive creative explosion over the last 15 years. This is a tiny snapshot of the kinds of things that people in this field work on. And there's been a very nice synthesis over the last few years in the form of symmetry indicators and so-called topological quantum chemistry that provide a symmetry-based approach to identifying or diagnosing type topology. Just to give you a picture of where we're going with this is all of these topology things appear in tight binding models. Some subset of these have topological band structures, and some subset of these have symmetry indicated topology. But this is a large bite out of this, or at least it seems now to be a large bite out of this blue region here. And these are the papers that we're resting heavily on here. These are mainly devoted to electronic systems, resulting in a gigantic materials database of proposed topological materials based on electronic band structure calculations. And here there are two works, one from Ohio State and from us, trying to adapt this to magnons. So what's the basic idea here? The basic idea is that you have, so please ask questions as we go along. You have trivial, we have trivial bands or topological bands. Trivial bands have the property that if you try to find maximally localized orbitals out of these trivial band structures, you can do that, preserving all of the symmetries. These are so-called maximally localized one-year orbitals. For topological bands, this is not possible. This is known in the context of Landau levels for many years, and it's essentially a defining property of topological bands. So how is this useful? How does symmetry connect to this? Well, what we can imagine doing is using the fact that you have localized orbitals plus the requirement that they should form band structures using only symmetry constraints to build all possible band structures from all local orbitals for all, in principle, magnetic symmetry groups. That sounds like a massively ambitious task, but if you could do that, then any bands that could not be so constructed should be topological. That's basically the idea motivating all of this. So you essentially, in some sense, by exclusion, see what bands should be topological.
Okay, what's the cartoon?
Oh, this is a very silly cartoon. This is supposed to be this old trope of the donut and the coffee cup. Yes, exactly.
It's a donut, like a universe, like a galaxy.
Cool, yes. Okay, I had a less profound interpretation of this. Okay, so anyway, so what we're going to be involved with here is just the basic symmetry elements of the lattice. So these can be point group operations like C3 rotations, translations from one lattice point to another, and combinations of these, all together forming a space group, which can be enlarged further with time reversal to form a larger group.
Sorry,
yes?
Are you considering metallic insulators? You're considering conducting systems right now?
I'm considering, well, okay, my motivation is really for magnetic insulators, but these symmetry ideas should hold for all magnon systems. I mean, it's really independent. We just need to have a picture where the localized, there is a decent localized magnon description, which will not be true for all metals, but certainly for some metallic magnetic systems. Yeah, okay. So what we're going to do is use these combined ideas of locality and the requirement that we need a band structure. So what we do is we look at single sites. These are where the localized orbitals live, which for magnons are just the transfer spin components. we have some kind of site symmetry group. So the group that leaves the site invariant, maybe up to translations. This thing is isomorphic to some point group. And we put some particular local orbitals there. And then we carry out a process called induction that leads to the full magnetic space group. So we take the irreducible representation of these, which is the defining property of these, which is the way that these local orbitals transform, and then just take this to the full group. So what does this actually mean in practice? It means that we have some large matrix indexed by different k vectors in the zone. So this breaks up into blocks, each individual block for a given pair of k's. So different k's can map into one another under the larger symmetry group. But an individual k vector will have internal blocks that depend on the number of sublattices and the dimension of the irreducible representation. And this encodes essentially the entire symmetry information within the band structure in a discrete way. Really, there's a discrete number of momenta because there's a discrete number of high or low symmetry points. So this is some kind of skeleton of a band structure. So instead of some continuously varying bands, we have discrete points and information about the connectivity of those points. Now, for magnons, so I need to keep track of time here. For magnons, in the presence of strong spin-orbit coupling, so we're going to deal only with the strong spin-orbit coupling limit where we saturate the interactions with all of the anisotropic couplings allowed by symmetry, like in the Kitaev model with gamma terms and so on. And we rely on the invariance of the magnetic structure, which forms some magnetic space group. And we know that the local orbitals are these. So using these ingredients alone, we can, in principle, build up these so-called band representations, so that these things on the previous slide, from all of these local orbitals, and construct all of those one-yearizable band representations for all of these 1,651 magnetic space groups. Now, this has been done. So this is a tool that we can use. And let me just give you an example of how to do this, going back to this Kitaev-Heisenberg model with the gamma term. Let's just forget the microscopic. So there's no model. There's just a magnetic structure with the symmetry of the lattice and with invariance of the magnetic texture, like this, with the moments pointing out a plane. The magnetic space group here is this one. It doesn't matter what these symbols mean, but these are all tabulated. You can simply go from this to this. And then using the local orbitals, we can identify what the local irreducible representation is for this site symmetry group, for this magnetic space group, and induce to the band representation. And it turns out that this band representation consists of two bands, and those bands do not need to touch one another. Now, what we know about these elementary band representations is that altogether they are one-yearizable, but they are the atomic units of one-yearizable band structures. In other words, an individual band here cannot be one-yearized, or at least one of these bands cannot be one-yearized. In other words, at least one of these is topological. And it turns out that for this case, purely using these discrete points, you can compute the Chern number for this skeleton of a band structure just using the symmetry data. So there's no model, you just get this topology falling out of symmetry. And, but in the end, what you want is to connect to actual materials. So what we can do is just write down an exchange model that respects these basic symmetries, that constrains the interactions that you can have between the moments, and then you can just stabilize the structure, and that's it. You have the band topology in your model after you remove accidental degeneracies. That's a very good question. This is nearest neighbor exchange. In principle, this will not always work, but the principle is you start with nearest neighbor, you saturate the interactions by symmetry, and then you stabilize the structure, and then that's it. Then you're done. It may be that you need to go to further neighbor to remove accidental degeneracies, for example. You can also play this game with nodal topology. There's a kind of menu of different things that you can get, and if you look at our paper, there are extensive lists of where you might find them. Here's just one example. Suppose you want to have 6-fold nodal points. Then we just look up in the tables. We find this magnetic space group with this site symmetry. And then we can just write down a model saturating the interactions, and there's the 6-fold degenerate point, and there's the magnetic structure. So it's inverting what we usually do. Okay, I mean, I can stop there and take questions.